Hey guys, welcome back to another episode of Simuleos. Today we're going to continue working on the Huffman trees like we've been working on for the past, well, little bit. So we've been on and off with this one. I think today we're going to finish up the visualization of simple Huffman trees, and then we'll see where we need to go from there. We can do a whole bunch of things with the visualization that we're probably not going to do on stream, but will be done off of stream, and I haven't quite decided the best way to do all of that. So we might get into some of that, but I don't think that is particularly interesting. Okay, so first things first, before moving any further, I want to point out one thing really quick about some of the videos that I was working on yesterday, and those are the determinant videos that we did a while ago. Those videos turned out really nice, I think, and I kind of like what they show. So here's what I'm going to do. I'm going to CD into projects, Simuleos, visualization, and determinant. I did two different determinant videos, so let me do ls. And they are angle 1 and angle 2.mp4. So if we do mplayer, angle 1.mp4, loop 0, then we're going to do, what do we want to do? VO x11, so you guys can see it. We'll full screen it, and you'll see, okay, here's what we saw before, right? So I kind of made it so you can see the center a little bit, you can see the yellow, you can see the blue. I tried to make it so you could see all the colors just fine. In the end, it looks okay. Then we have another angle, which is angle 2, which you guys have not seen yet, which I think turned out pretty well. So this one is kind of nice because you can clearly tell that this transformation transforms more along this direction here and this direction here than that direction there, which is what we should see, because this direction here is just -1, so we get the same value out that we put in, just the opposite of that. These values here are 3 and 3, so they should be 3 times as big, and indeed they look like that. And then after performing the integration, you can see, okay, we have all the blue and yellow and red. I think it looks pretty good. So what I want to do when I actually do the video is show both of these guys at the same time, right? So I want to show one transformation and then the other transformation, and then obviously the integral after doing it a couple more times than shown on this video here was exactly 9. Sorry for the yawn, guys. Was exactly 9, and that was exactly what we wanted to see. So this is pretty good, I think. So we have these two different videos, and I'm quite happy with how they turned out, I think. So we'll go from there. So those are the videos that I'm probably going to show on the determinant video. There's one more video that I'm probably not going to show on stream because it's relatively straightforward how to do that one. All we have to do is take a couple different eigenvalues, or eigenvectors, sorry about that, put them into positions so that when they stretch after the transformation, they'll form a cube that we can look at the length, height, and width for. And that's about it. So this video, actually the next determinant video, is going to be a little bit shorter than a lot of my other videos, just because I don't see a reason to make it particularly long. I think it's okay to keep it kind of short. Okay, so now let's go ahead and CD back into the Huffman directory. Now, as of yesterday, we did the following. So let me go ahead and open it up. So let's do, what is it? Mirage, frames, animation.gif. Okay, so we have all these dots being appearing, and that's great. That's exactly what we want to see. Now the problem is that all of these dots are appearing at locations that make it hard to really tell what the tree is doing. So it does look tree-like, which is nice, but it doesn't really show us what's going on the inside. So what I need to do now is change the visualization scheme on X. But before we get any of that done, let's go ahead and start by talking about what Huffman encoding is and where we need to go from here. Okay, so let's do it. Huffman encoding. So the idea behind Huffman encoding is pretty easy. We take some sort of string and we convert it into a bunch of bits. Okay, so it could be any string, and the number of bits we want to be an optimal number of bits. By optimal, I mean smallest number, in a way. So the least number of bits possible. Now, if we don't know the string beforehand, the best way to do this is to assume that we have a frequency of all the letters that are coming in. Hey, Gustorn, so we have A, B, C, and D. And again, so A could have a frequency of, I don't know, 0.6. B could have a frequency of 0.2. C could have a frequency of 0.1. D could have a frequency of 0.1. and these guys add up together like so. We add the two lowest to make 0.2, two lowest again to make 0.4, two lowest again to make 1, and then we just go and count them backwards. 1 0 1 0 1 0. So A is 1, B is 0 1, C is 0 0 1, and D is 0 0 0 1. And there you go. We just did Huffman encoding. If you have any questions, comments, concerns, let me know. I'm just trying to kind of give you guys the idea before continuing with the stream. So that's what we have there. No problems whatsoever. Now, if we were to encode something like A, B, C, D, this would be 1, 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, right? So we did 1, 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1. And this is really interesting, right? Because you can already see that we've got some compression here, right? Because if the A's were anything else but 1, we were going to miss a couple bits, or rather we were going to add a few more bits that were unnecessary to this particular encoding scheme. And that's something that, you can immediately see why we'd want A to be a smaller number of bits than B, C, or D. Okay, so that's that. What are we doing today? Well, today we want to visualize the tree, and we've got a good bit of stuff done, right? We can draw all these dots. That's fine. We can connect all the dots. That's fine. All of the connection points go under the, I don't know, this is a very poorly drawn tree, but all of the connection points clearly go under the, how do I put this? Under the dots that we've drawn. However, the dots are not located very well along X. So we have to figure out the best way to locate them along X. And there's a very interesting way to do this. And the way that I kind of chose to do this was suggested by Gustron yesterday in a link. So, well, he gave me the link and then I went from there. So we have the root node. If we can figure out what the farthest right node is and the farthest left node is, then what we can do is we can go through and figure out what this maximum distance is, right? And if we can figure out what this maximum distance is, then we can do something pretty easy. We just say, okay, we're going to move this far to the right, and this far to the left, and this far to the right, and this far to the left, every time we create a new node. So before, what we were doing is we were saying, okay, we have all of these nodes, let's just kind of place them down in such a way that we know that there will be no, that none of the nodes will be outside of the region that we're writing to. That worked okay. However, it wasn't necessarily the best way to do it, because we ran into the situation where some of the nodes would overlap other nodes. So we need a way to space all the nodes so that they look nice together. And also we need a way to make sure that none of the nodes go off the screen. So to do that, all we need to do is find, I guess, this isn't so bad. All we need to do is find the longest length strings, and then after finding the longest length strings, go through and count the number of ones and the number of zeros. The number of ones will be the number of movements to the left or right, I don't remember, and the number of zeros will be the movements in the other direction. And then that's all we need to do. We can find the maximum distance from there, and then we just, we just plot them out. So this should take probably the first hour, and we'll see how long it takes and what it looks like after that. And we'll go with this visualization from there. Again, there's a lot of things that we can do after that point, and that's pretty interesting on the one hand, because there will always be more things to do. But the question is, do we want to do them on stream? That's something we can do a little bit later, or we can discuss a little bit later, depending on how long it takes for me to do this new exposition. Okay, so let's go ahead and bring this over to the next desktop. Let me bring up the animation so you see where we're at right now. And again, you can clearly see that some of the dots are overlaying each other. So this is something we need to fix as soon as possible, hopefully. Okay, so let's go here. Let's CD into projects, Simulayos, and Huffman. LS. Now what we need to do is, what do we want to do? Go to Huffman visualization.cpp. Huffman visualization.cpp. Okay, so now what do we need to do? Well, there is a function called find x position down here somewhere. Find x position, here it is. this is the thing we need to fix. So we're reading in a bit string, right? And we're reading in the frame animation. That's fine. However, I think we need to find X position a little bit differently. So we've used this function twice. We've used it here in the depth first search algorithm to figure out, one second, how far we need to go along X and Y. So we use the individual bit string to tell us that. We're going to use a very similar method here. So we used it there, and we also used it here in the draw external nodes. So we used it once for the external nodes and another time for the internal nodes. And basically, by using it in the depth first search algorithm, we were able to figure out the X location of, let me see, where are we? Depth first search. So by using it here, we were able to find the X location of each of the individual nodes and go from there. So that's kind of the idea. Okay. So what do we need to do next? Find X position. Find X position. Okay. So we read in, also think you should use one Y position per tree level. Makes it look nicer. We are using one Y position per tree level. I think. I mean, we should be. That's, yeah, we totally are. Okay. Yeah. So this one's up here. Then we have these. Yeah, it should totally be the same. Yeah, okay, good. No, I totally am. That's how I did it. Here, let me go here. The Y positions are determined by the weight. So what I did, look at the two children of the root node. Yeah, those are two different levels. They're determined by the weight, right? Oh, wait. You want them determined, when you say tree level, you don't mean weight. I see what you're saying. We'll see what happens there. I thought you meant weight by tree level. Sorry about that. I kind of want to keep them with weight. It makes more intuitive sense to me. But we'll see what it looks like after we do the X visualization. So, but we could do it by tree level. I just, I don't know. I think it tells less information. We'll see. Okay. So let's go down here. And let's see what we need to do. Animate line, where am I? Grow circle. Where am I? I was just doing find X position. Okay. Let's go down here. So we have the individual bit string. All we need to do now is read how far we need to go, right? So we need to read, I guess, the maximum number of ones and zeros, I suppose. So let's think about how we want to do this. So find X position. The weighting difference is so little that it only makes the tree look a little weird for me. That's fine, but I don't know what it's going to look like when we add in the X position stuff. I suspect that after adding the X position stuff, everything should be fine. I mean, it seems to me that... Anyway, we'll see what happens. Okay. So what do we need to do? Let's do... Gosh, I'm having the hardest time thinking this morning. So, string, bit string. We're reading in the string, bit string. But what we should probably do is also read in the entire list of bit strings. So find X position. Let's do string, bit string, and let's do this. Or what we could do is read in the dx value, I suppose. So let's do that instead. So here, where do we do find X position? And find X position, depth first search. That would mean we'd have to read in the dx value with each of these depth first searches, which is kind of a pain in the butt. Okay, is there a way to do this by only reading in the bit string? Let me think. So if we read in just the bit string, this is the encoded 1010 whatever it is. We can find the number of ones and zeros, but that doesn't really help any. Yeah, that doesn't really help any at all. Okay, so let's go back to find X position here. And let's just write a function. Where is it? There it is. Okay. So I would say we need to read in a dx value. So we'll do double dx, which is basically the difference between every single point, I suppose you could say. So like, as we're going down the tree, we'll say dx is, this way and that way and that way and that way. So it's the distance in x every level needs to go. Okay, so now we go here. Let's go ahead and comment all of this out. Here and down here. But we're going to use something very similar up here. So we're going to say double x position is going to be equal to animation dot resolution x divided by 2.0. Now what we need to do is say for size t I equals 0, I less than bit strings dot size I plus plus. Okay. Now, I think we should probably just actually do the interior here almost exactly the same. So let me see, what did we do before? We said x position. Okay, yeah, okay, so let's go ahead and take this and let's put it in here. Except this time, rather than doing the x position plus equals animation dot resolution x divided by 2 times the power of 2 double I plus 2.0, which is what we did before, we're just going to say x position is going to be plus equals or minus equals dx. And minus equals dx. Okay. Now let's go up here, and just for the sake of the argument for this particular guy, let's just go ahead and give it a random dx. So let's go here and say, I don't know, I'm just going to say, let's say 50. Next, double dx. Next, 50. Next. Okay, write this, go down here. And let's go ahead and quit this and make it one more time. Okay, lots of errors. Let me go to 355. Let me see. Oh, okay, I forgot to close it down here. Anim cannot convert frame to double in initialization. Let me see, 342. What? How did that turn into double X position? Oh, okay, I see. I wrote that again. Let's go here, make. And it seems to be running just fine. Now let's open up the animation one more time. And let's see what happens. 1 second. Give it a second too. Okay, there we go. Mirage animation frame.gif. Okay, so these are all the guys appearing. Okay, Okay. Let's see. Well, they clearly have defined locations now. Let's go to where we put all the 50s. Let's see, one here. Let's change this to 25. Next, 25. Next, I only put them twice. So let's do, oops, sorry about that. Make one more time. And obviously we need to fix this in just a second. I'm just trying to check something out for now, just to make sure it kind of looks okay. And then we'll go from there. 1 second. Let's, there we are. Mirage animation frames.gif. Okay. So we're running into the same situation we ran into before, where some of the dots are just being drawn over the other dots. And I'm not sure exactly why that would be the case, unless, you know, the Y positions need to be fixed too. So let me think. We have, so if they're of the same weight, let me think. Yeah, I guess this would be if they're of the same weight, right? So, hey, FAFSA, let's go ahead and do what Gusfern suggested with the Y positions, and let's see if that fixes this. So let's go down to where we do the Y positions, and then we'll go from there. Where do we do the Y positions? I think the Y positions are in their own, or in each individual function before the find X position. So where are we? Find X position. 1 second. Here's X position, X position, X position. That's all fine. Where's Y position? There it is. So here's our temp position.y. Let's go down here. Let's do temp position dot y. And how are we going to find the temp position dot y? Well, it could be, let's see, instead of root, let's do what we did initially, which was give it a position based on the following. So let me go up here. Do we use lowest location anywhere else? Location. There. And it looks like it's just used and draw internal and draw external. Okay. So let's go and let's redefine how we do this. So next, here we are there, and there we are there. So we're going to say lowest location is going to be equal to, let me see, what do we want? We initially had it this way, but then we changed it a little bit later. So let's do, where did I do it before? I think it was 4. What do I want? We have the Huffman tree, and we want to go through the bit strings. So we'll say, is bit strings a vector? Let me see. Let me go into vi Huffman .h, and let's see what we got here. So let's go down to decode, what do I want? Huffman tree. And it looks like we have an unordered map, but we also have the bit map here. And we have the character and we have the string. So I guess we just go through all of these guys. So for, let me think. We have the std string. Is that what we need? Let me see. Or is it the character that we need? For, I think it's going to be character, key, in, let me see, Huffman tree dot bitmap. We go down here. Okay, so let's go, let me see. We'll say, how do we do this? Lowest location. Equals, we'll just say 0 for now. And then we'll go down here and say, if, let's see, key dot first, let me see, dot, I guess it's dot second, dot size, is greater than lowest. God, I cannot code it all today. Location. There we go. Let's go here. Let's change this to an underscore. Then, lowest location. Is equal to. Wait. The dx is exactly what. Well, okay, wait. I'll show it in just a second. I think once the y positions are fixed, the x position should be fixed too. So now we're going to do lowest location minus, what do I want? Equals, sorry about that. Key dot second. Okay. Let me go down here. Let me just remove this. Let me just see if this runs. I've got a feeling it's not going to. Let me do make, let me see. Yeah. So jar initialization. Let me go up here. Lowest location equals 0. I need an int there, or double. And let's go here and change this to auto. Make, let's see, key dot second cannot convert std basic char double in lowest assignment. Key dot second dot size is what I need. Make expected semicolon before temp position x. Let me go to 312. Okay, fair enough. So now let's go down here and let's do the following. Okay, so we're going to do temp position y is going to be equal to basically the bitmap. So let's see, tree dot weight map root. Tree root weight. 1 second. What am I doing here? I want it to be. Yeah, so I want it to be the length of the string. So we're going through all the bitmap. So let's do key.second.size, and we want a double of that, divided by. Yeah, I think I know what you're saying, because we ran into the same situation before, and this is the reason I did it the other way. There will come in multiple situations where you'll accidentally write over other dots. But let me change this Y position into something a little more standard, and I think that should help out a little bit. Okay, so we do key second size divided by, what do we want here? Lowest location. Okay. So let's do this, right, and let's go to make one more time, just to make sure it runs. And it does, but the animation is going to look like crap. So 1 second. Let's show that. And let's do Mirage animation.gif. Yep. Yep, that wasn't exactly what I was anticipating. That was like the opposite of what I was anticipating. Okay, let me see. Okay, we've done this before. In fact, we had a previous version of this code that ran very well with this. So let me go to my GitHub page, which should be, again, down here. Click on this. Go to Simuleos. What do we want? Huffman. Huffman visualization.cpp. Where is the history? Here's the history. Okay, so add a new Y location for the external nodes. We want to go to the previous one. So let me see, what do we have here? Node parent Y. Let me see. Lowest location equals log10 tree root weight. Nope. Internal and external nodes are drawn. Yes, this is probably the one I want. Actually, I probably could have found it in that last one, couldn't I have? Tree weight, let me see, node. Where are we? Node 2Y. We generated nodes. Let me see, where are we? Maybe go back to this one. Node parent, double lowest location, tree weight map. Yeah, okay, 1 second. I did something really silly here, and I'm not sure what it was that I did. But I know I fixed this before. Animate line, node parent Y. Okay, let's just go back and see if we can figure it out. Okay. So let's go here. The problem is that they're all being generated at the very top of the screen, which is kind of a pain in the butt. So let's see if we can figure that one out. So what we've done is we've gone through and found the longest, I suppose you could say, the longest bit string, right? And so that's going to be the number of times we go down the tree, right? So if that's the number of times we go down the tree, then what we need to do is figure out the number of times each individual guy has gone down the tree, and that's going to give us our new location. So what I failed to do here was I failed to scale this. So let's go here. 1 second. Let me put parentheses around this. Oops, sorry about that. And parentheses around this. And let's pop down here and multiply this by this guy up here. Right, now let's go to make one more time, and let's see those new Y positions. They should be upside down, but I think this should be okay. Okay, so now we have 1 second. Mirage animation.gif. Yeah, okay, so now they're in the appropriate, in an appropriate Y location, but they're not quite adding up correctly because the Y locations of the internal nodes don't quite match up. Okay, and then the other thing is, for some reason, here, let me see what we have here. I'm watching them. Yeah, so we're still overwriting some of them, which is a little weird, but that's okay. We'll figure that one out in a second. And I think this is exactly what I said before. Yeah, I think it's exactly what I said before, where we run into a situation where we accidentally overwrite the different pieces. And that's kind of why we did the X calculation a little differently. Okay, so let's go through and do the internal nodes now. And then we'll kind of go back to the drawing X location one more time. So what do we need to do? Animate line. Where are the other Y positions? So let me find lowest location. Here, I'm gonna copy this one. Next. Yep. Okay, here it is. So let's go ahead and comment this one out. Go down here, paste this. Now for each of these guys, we now need to do the new Y location like we have done for the other guy. So let's go down here. And what do we need to do? Basically copy this calculation. Where is it? Up here, I believe, somewhere. Yes, this guy right here. Wait, what? Determining the X and Y locations. That's not quite right. Double lowest location. Temp position Y is equal to... 1 second. What did I do here? I think I meant to comment this out. But for some reason I did it a little bit differently. I'm super exhausted today, guys. I don't know why. I got plenty of sleep last night, but I don't know. I've just been super exhausted lately. This is what we want. This guy right here. So let's copy this. And let's bring it down to the bottom. Okay, so where are our Y positions? Here they are. So let's go here. Let's paste this. And now let's change it to node parent Y. Are you part of the Yakuza? Not that I'm aware of. Sorry about that. Node parent pointing to Y. Okay. And I can remove one of those Y's. Move it forward a little bit. Now we have to do the same thing for node 1. Oh, sorry about that. Node 1 and node 2. So I'm just going to copy this. And let's copy it twice. Okay, so now we change it to node 1 and node 2. And node 2. Let's go ahead and remove a couple lines here, or a couple columns here and a couple columns there. And let's see, what do? We say node 1 wait, final tree root wait. Okay, so this is something that I need to figure out. So before I read in, let's see, where are we? Double Huffman tree, final tree. Before, I read in each individual weight. And that's fine, but it's not quite what I need in this situation. So how do we calculate the weight? We calculate the weight based off of... yeah, so the weight's not going to really help us here. What we need is the string size. Now we have the bitmap, which is going to be the map of all of the bits and stuff like that. However, again, this is a situation where we need to figure out where those bits are. So let me see. What do we need to do? We need to figure out how to find the size of the strings at node 1 and node 2y. But the thing is, some of them don't necessarily have strings, right? Oh, wait. When we drew the external nodes. Yeah, okay, this should be fine. So let's go here and change it to, where are we? Node parent.wait. Yeah, so let's just change it to node parent.wait. Wait, no, it shouldn't be node parent.wait. It should be node parent y. 1 second, let me think. It should be... Okay, so what we need is the following. We have a location for the underlying nodes. We definitely do. They are node Y. We're trying to find new node Ys. So the old node Y, let me see, node 1 is going to be key second.size, lowest location. Why are we doing this? We already have the node Y, don't we? 1 second. Node 1 is equal to regenerated nodes top. I'm a little bit confused here. Let me go down here. Let me comment these guys out. Okay, now let me go here. Node parent Y is going to be equal to, it should be just a mix of the other two nodes, right? So it should be that this is one level up from the previous two guys. So wherever we were at, the new Y location should be like 1 bit less. Okay. So how do we do that? We can say we have some sort of Y location, and then we add a little bit to it. That's fine. And what should we add? We have the lowest location, so it should be that we do okay, so here's what we're gonna do. If node 1 pointing to y is greater than node 2 pointing to y, we do the following. Else we do something else. Else we do something else. Okay, so this means node parent y is going to be, let me think. We have the lowest location, which will give us a dx resolution. So let's go down here and let's calculate a dy rather. So we're going to say double dy is going to be equal to 1.0 divided by lowest location. Okay, and then we got to multiply this by our scale factor. So let's go that here and let's multiply by the scale factor times 0.9 animation. Here we are with a semicolon. Okay, so now what we're going to say is node parent is going to be equal to the following. Node 1 pointing to y plus, oh sorry, minus dy. And now we do the same down here. We say node parent pointing to y is going to be equal to node 2 pointing to y minus dy. Okay, let's see how this breaks. It's going to break in a spectacular fashion because for some reason my brain's not working today. And so everything is just super hard for me to figure out right now. Let's make it lowest. Is obviously not a thing. Let me go to 397. I need an underscore. Let's go here. Underscore. What's next? 397, 391. Tree was not declared in this scope. Was it not? Final tree. Let's do this. Final. Okay, now let's make it one more time. I'm gonna get a quick sip of water. Man, I'm just so out of it. Like, I just can't think. Okay. Okay, it is converting it all into a graphics interchange format file. Now, let's go through here and let's see what we need to do. Mirage animation.gif, and let's see what the awful verdict is. So, it's not even drawing the lines. Good. Okay, that must be because originally when we define the Y position, we don't give them their initial Y positions, which is kind of a pain because I thought we did. So let me go through here. And when we do depth first search, what we're going to do is we're going to give them a Y position here. So if root key, then we go down here and we say root. 1 second. I'm having the hardest time with this one. We're going to do the following. So we're going to find the lowest location, and we're going to go ahead and give them a Y position. So what we're going to do is the following. So let's go up to the top here where we did the lowest location to begin with. Where are we? Here it is. Draw internal, that's fine. So if we're there, we do this. And let's go ahead and add 12 spaces to these guys. Oh, that wasn't right. 8 spaces. Okay, dot, 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 dot. Okay, so now we have the lowest location. Now let's go through and say root Y, pointing to Y is going to be equal to, we have the bitmap being read in, so why don't we just do the following? We're going to say bitmap bitmap of key oh, sorry, root pointing to key. That's kind of ambiguous. I apologize for that. Dot size. So this will give us the size of the guy we're working on. So then we need to do double. And now let's go down here and divide it by lowest location. Add in a parentheses here. And of course over here. And then let's give it this scale factor right here. Scroll down. And let's see what happens. Let me move it one space up. One second. I'll take a look at that in just a second, guest run. There. Write this, go over here. Let's write it real quick. Make final tree.bitmap not declared in the scope. That's because it is just bitmap. Make. Okay, seems to be generating all the images. Give it a second to move them all up. And then I'll take a look at your gist in just a second. Mirage animation.gif. Have all the points being generated. And they should be, yes, so they're all given Y positions. The Y positions all seem to add up. Okay, but they don't seem to add up correctly. That's okay, we'll worry about that in a second. Now let's take a look at the gist. Open link, what do we have? Let's say you have a tree. But work with normal coordinates. Left is the current level of the tree. Let X be a sufficiently large distance. Yeah, you're right. They do seem to overlap. So my question was, why over here do they not seem to overlap? Let me see. Not that one. I want this one. Okay, so what's the difference between what I just put down? Oh. I see. The problem is this guy only goes to 3 levels. You're totally right. Darn. Okay, well, this is something we have to think about. Let's go ahead and fix the Y positions, because they seem a little bit easier, and then we'll worry about the X positions in just a second. So let's see, what do we have here? The Y positions are kind of sort of adding up, right? You'll note every once in a while we have a straight line appearing. These straight lines are because 2 dots are superimposed on top of each other, and we're adding them together. Dang. Okay, so let's go and let's see what we need to do. Okay, so let's do it this way then. Let's change their X position back to what we had before, just to make sure that these guys are kind of sort of working. And then let's see if we can figure out a better way to draw those X positions. I thought this would be super easy. No, he doesn't. The algorithm right here does exactly what I wanted to do there, you know? So that was exactly what I wanted to do. Yeah, this one. Okay, so all he does here, it says right here, he finds the left and right contour, and then he decides where to place everything based on the left and right contour, which is exactly what we just did. So, yeah. Later on, he did something a little bit more confusing down here, but I can't read that. This is something I can read up here. So let's go through, and let me fix the Y positions, and then we'll worry about the other positions from there. So you see it just barely goes off the map at the top, and I'm not sure exactly why. Let me see, are these guys actually adding to be the appropriate location? No, they're not. So let me go to the DX position for the draw internal. Where's draw internal? Animate line, let's go to draw internal. And let's see, let's change it to dy. Let's change it to 2.0, why not? Let's just see what happens. Let's go over here, quit, and let's do make. Okay, give it a second to make all the images and convert it into a GIF. and then we'll go from there. Mirage animation. Okay, so now we at least have all the dots being drawn. All the lines should be drawn. Yeah, okay. I see kind of the problem here. This is going the opposite direction of what I thought. Let's go here. And let's do 0.5. Let's go there and let's make it. Maybe. Okay, so I guess I misread the article then. I'll go through and read it again later. But for now, we don't really have time to read it. So, let's go through and real quickly do... One second. Mirage? Okay, so this should be... Let me see. Okay, so I think this is the appropriate... Yeah, that looks like the appropriate size. So let me see. Let me see. You posted it here? Open link. Let me see. Okay. So let x be sufficiently large distance. After root node's position. After let each children x position be parent x. Oh, I see. After let each children's position be parent.x plus equals x divided by 2 raised to the level plus 1. I thought that's what we did. Yeah, I think that's exactly what we had before. Let me see. So let me do the x position. Where's find x position? So we said x position plus equals animation.resolution x divided by the power 2 raised to the double of I plus 2.0. Yes. So it's pretty dang close to what we had before. Plus equals or minus equals depending on what we have there. Animation dot. But you're saying parent of x plus equals. We did resolution of x. Let me see. Oh no, parent of x. Yeah. So this is actually the x location stuff that we had before. So let me go here. DD. Let me go here. And there. Right, go over here, and let's do make one more time. One second. We go here, Mirage, animation.gif. That's not a legal operation in C++, right? I'm not missing anything here. Okay, so let's go here, add these guys together. Okay. So it's supposed to be plus minus. I'm not sure I understand what the difference is here. I thought after, so let me see. Let x be a sufficiently large distance. Okay, let the root node position be x over 2. That's exactly what we got. After, plus if we step to the right, minus if we step to the left. Yeah, so that should be right. Because this is, I'm a little bit confused as to what you mean. After let each children's x position be parent of x plus or minus x divided by 2 raised to the level plus 1. And that's what we have here. So what we say, if we step to the left, where the bit string is equal to 0, we say, or it's right here. This is the code. So we say double x position is animation resolution x divided by 2.0, exactly like what you had before. Then it says for size t I equals 0, I less than bit strings dot size. So we're going through all the bit strings, or we're going through this individual bit string. We start with 0, and we say, okay, if the first one's a 0, which means we're going to be going to the, I guess I chose this as right. I should have maybe chosen it as left, but that's fine. We choose it as one direction, right or left, and we say, okay, well, now we go over some distance, right? And that distance is, in this case, animation resolution x divided by power of 2 raised to double I plus 2.0. If you redo 1.0, it's, I don't remember why, but we had to do 2.0. Let me see, what happens if we do 1.0? Let me do make. I think 1.0 was the wrong level. I think 2.0 was the right level. I don't remember why, though. Let's go real quick. 1 second. Mirage animation.gif. Let me see. Oh yeah, you have overlaps because the weights as y instead of the levels. No, we fixed the weights as y. We now don't use the weights as y. We now use the levels for y too. So everything is, what it was before. The overlaps in x. If ko, we are using just Cairo to do the animations here. So Cairo is a graphics library. We're kind of using it for animations and kind of teaching ourselves how to do that. Okay, so I think this was the problem. What was the problem here? Oh, wait. What OS am I using? I'm sorry. I just read, what are you using? We're using, in this case, Linux. It should be, yeah, it's Arch Linux. That's the distribution we're using. If you're interested, I'm not trying to push you into Linux or anything like that. Okay, so the reason I had to do 2.0 was because it went off the screen. But why did it go off the screen? Let me think. We had this figured out at some point. Let me think. For I less than bitstring.size, animation resolution x.2.0. And again, the problem here is just that we clearly see overlaps in x. Let's change this back. Go over here. And let's, oh gosh darn it. And let's do make. I still Linux, wonder what distro. I'm using Linux myself. So let me go up here real quick to Mirage. Okay, so again, we're kind of sort of, I don't know if it's any better than we were using the bit strings for the visualization. Yes. But the bit strings directly relate to the string, right? Or to the tree, right? So what's the difference between using the bit string and the tree? Because if we use the tree, we're going to get the same exact visualization. We should anyway, assuming that yeah, right? Because in the end, one second. In the end, the tree is, we get the bit strings from the tree, right? So I'm not sure I understand how that would make a difference. Sorry about that. Okay. Okay. So let's see what we got here. What we need to do is figure out how to revisualize the tree. Now, we had an idea, but apparently the idea didn't work out the way I thought it would. So we have to do something else here. I'm not sure what else we can do. We can, of course, increase the X resolution. That's fine. But that's not really going to help us in this situation that much. The problem, again, is that we're overlapping, like, for example, down here, 4 different dots in the same location, basically. So let me think real quick. We have a situation where, let's do page, new page before. This is how we're visualizing each X location, right? So we're saying we start off here at 0.5, then we go down here and we add 0.25 or 0.75. The next iteration we'll have down here or over here, and this will be 0. Okay, so it seemed to me that maybe 1.0 was correct. Let me think. How do I calculate the internal nodes? One second. The internal nodes are calculated by simply taking the 2 Y locations of the external nodes, which was determined based on the tree's location, and then from there, let me think. From there, adding in some sort of dy, which is related to, again, the maximum size of the string, which I think is fair enough, right? Because if we go, let's say we have a tree that goes like all the way down here, then we have 1, 2, 3, 4 levels, and the bit is going to be clearly 4 in size. The bit string will be. So it might be, I don't know, let's say 0, 0, 0, 1, 1. So that's 4 in length. And then we say, okay, we go left 1 to 0.25, left again to 0.125, right to, 1 second. I don't know if I can calculate this correctly. But we're running into a situation here where all of the internal nodes add together. Let me see how many final levels we have in the animation. So let's go over here. We have 1, 2, 3, 4, 5, 6, I think 7, 8. Okay, so we should have a maximum of 8 bits. So let's scroll over here. Let me see what we have. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Looks like 7 bits are the maximum number, but I guess that's fair enough because the root node was 0. You should just draw the tree as a regular tree. Don't draw the letters into internal nodes. Wait, what? I don't know what you mean. I don't draw the letters into internal nodes, so far as I'm aware. Yeah, so far as I'm aware, I don't think I do. Let me think. So, you draw the tree as a regular tree. Don't draw the letters into internal. Make your life harder by trying to visualize the bit strings instead of the tree itself. But visualizing the tree itself doesn't make sense to me. I don't understand how we would do that. So the problem is, if we need an XY location to draw from, right? So if we go to each individual node, right, and we go through like our recursive depth first search guy, right? We can't draw it from the leaves up. We have to draw it from the tree down. So what we have to do, or from the root node down. And so what we need to do is we need to at least get the locations, right? Which is what I did. I went through and I found the locations of each of the final nodes at the bottom, right? So I think, I don't know, I think this is fine. I don't, oops, sorry about that. I think it should be okay. Here, let me open up the window. Okay, so let's go through and let's see if we can figure this out. First of all, we don't know what, but it doesn't say anything. You know, we go through, we get their X positions in exactly the same way that we got our X positions, right? In the end, this X position will be the same, you know? Okay. So let me see. Yeah, but these X positions are going to be the same X positions as the X positions that I got. You know? Like, this is the same algorithm. You know? Doing the same thing. Yeah, we do. We treat the external nodes exactly the same. What? We treat the external nodes are treated exactly the same. We use the same find X position for the internal nodes. Where are we? Internal nodes. Draw internal. Okay, wait. So we have 1 second, internal nodes. Node parent wait, where's our find X position? Node 1X. 1 second. Okay, here's our depth first search to find our initial positions. Now we go up to internal nodes. Yeah, we're using the same for, I mean, it is the same, basically. So let me do draw internal. Let's go here, draw internal. Okay, so we have node X. Where's node X? Wait. Node parent X is... 1 second, let me think. Maybe you're right. Oh, I think you're right. We are using a different one for X. Let me think. I added them together and put them halfway together. The internal nodes should be at the exact same level as that of the leaves. I think they are, aren't they? Okay, yeah, they're a little bit lower. One second, let me think. Okay, so we got to figure that one out. They're a little bit lower because I kind of modified this. But it is the same guy in the end. So double dy should be 1 divided by the lowest location, but for some reason that's not right. So I'm trying to figure out why that's not. So see if we do it with 1 instead. Let's go over here and let's do make. Then it's for some reason off a little bit. And I'm not sure why it's off a little bit. So that's one thing that we need to figure out. I'm not exactly sure how to do that one. So let's go over here and let's see. But the thing is, if I go back down and I don't know, it just doesn't. So we would have basically a whole bunch of nodes. You automatically get the correct Y positions. What? This should work. It's not working because I have it off by some sort of weird factor. Let me go here. Let me say double dy instead of, let me think. So it's off by some factor, right? So we say node parent Y is going to be, where are we? Node parent Y is equal to node Y minus dy. Yeah, so basically we're adding in the dy. So where is node Y? What we should probably do instead is, let's see. So what we can do is we can take node1.y, and then we can, let's see, we have some sort of scale. So if we divide it by the scale, we should get an integer again. And then we can subtract 1 from the integer and multiply again by the scale. But that's kind of a weird way to do it. So let me think. Okay, so let's go here, page, new page before. And let's see what we need to do. So we have a situation. Each node Y location is going to be equal to some sort of integer. So we'll say, I don't know, 9 times the scale factor. Okay. So what we need to do is find the new location of the parent node, where the parent node's location will be, in my opinion, whichever one is the highest. Sorry, Fasta. Whichever one is the highest here. So let's say we have 2 nodes, one here and one here. We need to add them together. Then it should be something like this up here, where it's one level. So here, this is level L. This is level, let's say L minus 1, and this should be L plus 1. Okay? Sorry, I know today's like super scattered. I don't know how to really help with that one. I can try to draw it recursively. In fact, we did try to draw it recursively, right? So we got... Yeah, so what we did before, in order to find the initial Y locations, we went through and we did our depth first search algorithm to go through and try to find the initial Y and X locations of the external nodes. And that's what we did, right? So we went through a recursive algorithm to find the X and Y locations of the initial external nodes. From there, we have to figure out how to get to the internal nodes, which is hard to do recursively because we have to draw it from the bottom up. I mean, I guess we could put them all into an array or some sort of vector of all the positions. But that's not exactly trivial. So let's go through here. Let's see. So we do L plus 1 is here. So how do we get to L plus 1? Well, we're at L right here. So let's call this, instead of 9, we'll call it L, which is the level that we're at. I don't know. I also kind of like the fact that I I like drawing them based on the weight. I don't like drawing them based on the level. Because when we draw them based on the level, we don't tell them how much is under each of the... You know what I mean? So if we draw them based on the level that they are progressed down the tree, that's fine. But then I have to actually draw the internal nodes. And I have to say, hey, this is what the internal nodes are. And I don't like that. Because now if I draw a scale on the side here, and I say what this means, this is level, that doesn't really tell us anything. If this was weight, I don't know. I like weight. Let me go back to the weight visualization real quick, and let me see what we have. Okay, let me go over here. And let's see, node Y. Yeah, I don't know. It just, I want to. I don't know if I like visualizing based on the level. Let me see. Let me go back to what it was before with the weight, and let me see. Does it? I think it makes it look. It's more physical with the weight. Let's see. Node 2Y. Let me go up here. Hey, Devin. This hasn't got much to do with the project, but would you suggest for reaching maximum intelligence? I have no idea, man. I can't help with that at all. Let me just go back to see what it looked like with the weights, and then we'll see what looks better. So let me do draw layers, depth first search, regenerate nodes. No, that's not what I want. So let me go down here. Let me change the root Y here and there. Okay, now let me see. What else do we have? Regenerate nodes. Oh, I mean, that's fine, but I wanted to put a scale on the side to say what each thing meant, you know? Let me see. Draw external. Yeah, this is what I need. So let me go here. Remove this. Go down there. And go down here. Okay, so now we do temp position Y. This, what I need to do is comment this one back in and comment this one out. Okay, let's write this, go over here. Let me run make one more time. Error, okay, I screwed something up. 296. Yes, of course I did. Okay, let's try this. Make. Okay. We have some unused variables, but that's okay. Now let's see. What do we have? Okay. Now we do Mirage frames animation.gif. Okay. Well, that one's broken. Like, this one's clearly broken. I mean, but the weight isn't that different. Well, it is that different, actually. So I did something stupid with this, and I'm not sure what I did. Let me go down. Let me do the draw internal command. Draw internal. Let me see. Node parent weight. Let me see. Node parent X. Node 2, node parent new node. Oh, I guess, did I forget to... Let's... I don't know. I don't know what I did. Let's go here. Double key second. Node parent X. Oh, I guess I need to do this. Comment it out down here. Node 2Y. There. Something like this. Maybe. Let's go here. Let's make that. Okay. So now let's see how this one broke, because it's definitely going to break again. Okay, let's see what we got. Sorry about this, guys. I intended today to be kind of quick, but now I've got a feeling that I'm delving in forces. Yeah, I think that looks pretty good. If you want to emphasize probabilities, it'd be way more understandable if you had the internal nodes in, like, dotted circles. I mean, I can draw internal nodes. That's not the problem. If you want to focus on the leaves, leaving off the internal nodes. Wait, what? I want to draw drawing a Huffman tree, right? So the idea here is what makes most sense. And honestly, with the weights, I mean, the difference is negligible. You're right, in the end. Let me think. So if I were drawing a tree, so new page of 4, what I typically do is the following, which obviously is not the best way to do it, but this is how I always normally do it. I just put all the leaves here. So I say, A, B, C, D, E, F, and then I just say, these are all of our leaves, and then I'll add them together, something like this. And that's fine, right? That's typically how I do Huffman trees. I always do them this way. I don't usually have these different levels of visualization to deal with, but I don't know. So the other thing is the way that we're currently visualizing it, new page before. If we visualize it based on the level, what are we telling people, right? We're telling people how far down the tree they need to go. But in the end, we want to do the dynamic Huffman stuff, right? So the dynamic Huffman stuff, the Vitter stuff. 1 second, I'll take a look at that in just a second. What? Open link, there we go. Okay, so let me think. If we want to do this, if we want to do the dynamic Huffman stuff, we need a way to visualize the weights in the Y direction. Because every time we redraw the tree, the Y positions will change ever so slightly. So for example, if we have a tree that looks like this, let's say node here, then nodes here and here, and here and here. This is different than this, right? But if we just go down the level of the trees that they've traversed, then these are the same, right? So I think that was the reason I wanted to do it based on the weight instead of the level that we go down recursively. Because when we do the dynamic Huffman stuff, we really need to pay attention to the weights, right? Let me think. Okay, I'll take a look at the code. 1 second. Okay, so let's go here. Open link. I think I already opened it, didn't I? 1 second. I think I have a couple extra tabs open. Let's go here. Okay. So if node draw tree node, draw tree Cairo draw point. Okay. If node left, draw tree node. 1 second. Okay, so what you're saying is we go through, we do Cairo draw point. Okay, so what we need to do is put Cairo draw point under the... Okay, so then we do node x. What do we do with x? X minus x divided by 2. Yeah, okay, so let's try this then. Let's see, distance is some arbitrary maximum distance at the lowest level. I need all the leaves drawn first, and then I need the lines drawn after that. So what we need to do is instead of returning back, I need the leaves drawn first. So, Yep, I'm completely lost. So I don't know how this would work. So if we draw... We'd go through and we draw each individual point. That's what this would do, which is fine. But, let me think. Would this allow us to go through and, gosh, I need to draw the leaves. Then after drawing all the leaves, I then need to draw the rest. No, you're fine, Gustorin. We can modify it though. Let me think. So we have the X positions. How are we currently finding the X positions? This actually is probably much better for finding the X positions. Yeah. Let me see if we can do that. So we have draw internal. Let me go down. Let me see. What do we have? What do you currently read in? You read in level. Okay. So let's go through ours because ours is probably a little bit annoying. So what do we do? Find X position here. No, that's not what we need. We don't need find X position. Where do we do animate line, grow circle? What am I doing? I need depth first search. Depth. Here we are. Okay, depth first search. Okay, so if root right, if root left, then we give it an X and Y location. So what we need to do then is we have the animation frame, depth first search, we have animation root, regenerated nodes, and bitmap. So let's change this algorithm real quick. So let's change it to exactly like what you said before, draw tree. But I think I already have draw tree as one of the guys. No, I do not. So let me go down and let's do this. So instead of depth first search, we're going to say draw tree. So void draw tree. Okay, so what are we going to need for this one? We're going to need, I think anim, which is going to be the frame that we're working on. Let me think, is that true, or the layer that we're working on? Or we could just give it an initial X location. Yeah, so how about we give it exactly like what you said? We give it an initial X location. So we're going to say, one second. What you want is a reverse level or breadth first search? Maybe. Okay, so let's go through and let's do it this way. Because we still have to split up the drawing of the external and internal nodes, I think it's best to go through and actually, let me think. We can get a location for each of the nodes. Yeah, and then give them each a location along X and Y. So let's just give all of the external nodes a location along X and Y, and let's check to see how different this is from what we already have. So let's do the following. We're going to give it an X location. So let's say double X, which is going to be assumed to be the resolution over 2. So it's going to be half of the resolution. Okay. Now what do? We do double X, and then we say level. I guess we want this to be an int. So let's change it to an int. And what else did we need? We needed the node. Yeah, of course we need the node. So let's do node star root. Doesn't matter. I don't remember what order they're supposed to be in, but that's okay. So now we go down here. Okay. So the X position is going to be whatever we read in at the start. And let's see. If there is no root right or root left, so basically we're going to copy this down here to give it an X position. Okay, so let's do this. If there is no root right, and there is no root left. Okay, so this means we're at an external node. Let's go here, and let's do the following. Okay, so if root key, how did that happen? Oop, my bad. Okay, let's go back to the start. You could draw the whole thing during generation. You might be right. Let me think. So I have these two different functions. See, how do I do the Huffman stuff? We do the priority queue stuff. Yeah, actually we could. Yeah, so that's what I wanted, something that closely resembles how the tree is built, and that's exactly what we need. So let me go through and think about that real quick. So let's redraw this guy here. Yeah, so let's redo this guy to give them all initial X locations. And then we'll go from there. Yeah, I think you're right. This is probably the best way to do it. So we want to draw all of the nodes. Hey, Clone Style. So we want to draw the nodes initially. And then after that, we have a location for each of those nodes. And then what we need to do is go through and redraw the tree. Yeah, okay, so let's see what happens. Let's go through and let's get these nodes an initial X location first. Is that right? Maybe it's right. Oh, your root key. So we don't need this guy anymore. And we're going to say root X, which is going to be the next level, is going to be equal to whatever X it was before. Let me see. You have, let me think. If root key. So if there isn't anything, root X is going to be equal to, I think it's just going to be equal to X. Okay, now what we do is we go through, and let me see. If, let's say root right, then we go down here and we say X. It's going to be equal to, I guess, plus equals X over 2. 0.5 times X. Is that right? Let me check. Sure. Then we perform a depth first search. We do we need the level? What is the level for? Oh, the level's for the Y position. Okay, yeah, fair enough. Okay, so let me go down here. Okay, and we'll say in the utmost if, oh, thanks. So let's go here, and let's do that. And now we're gonna say, we want, draw tree. Wow, that didn't work out. Draw tree of, what do we want? We want X. We want root, I guess. No, we want right. Sorry about that. Right. And then we want level plus 1. Okay. So let me go through and just make sure this draws the X positions correctly, and then we'll worry about the Y positions in just a second. Because you're right. Right now we don't. Here, let's just go through and let's fix this up, and let's see if we can get the X positions done. So let's go here. 1, 2, 3, 4. Draw a tree. Okay, fair enough. X plus 0.5 times X. And let's change this so X minus 0.5 times X. And this will be left. Okay, let's see if this gets us the initial X positions okay. So actually, we need to do one thing first. Let me write this, and let's put the draw tree command up top. So the draw tree command should come basically next to main, and then we'll go from there. So let's go here, draw layers, function to get X and Y positions of external nodes, and let's go there. Void draw tree there, right, and let's do make real quick. Make. Okay, so let's see what happens. Obviously there's some unused variables, seems to write just fine. Now let's get those X positions and let's see what they look like. Mirage animation.gif. These guys look, dang. Okay, wait, why are we not drawing the internal nodes? 1 second. Depth first search. Regenerate nodes. Oh. 1 second. Draw tree. What do I need? I need double X position, which is going to be anim dot resolution X. divided by 2. So times 0.5. 1 second. Where's root key? Oh, probably fair enough. Okay, so animation, then we want root, and then we want 0. Okay, so let's put this there. Let's delete this guy and that guy. Good. Right here, now let's go to make. The best thing to do about this is it can draw leads and internal nodes at the same time. Let me see. Resolution X, what did I do with that? Did I put an underscore in resolution X? Maybe I did. Let's make, and let's see what happens. Okay, here we are, drawing all the things. We're good. Now on to the next step, which is going to be, let me see. Mirage animation.gif. Okay, this one draws all here in the same locations as before. Then we don't draw the internal nodes. The best thing about this is that it can draw leads and internal nodes at the same time. Let me think. How would it do that? So node queue regenerate node. I think I commented out the wrong depth for search. Let me DD here, there, and let me look for depth here. Now, interesting. Why? 1 second. So what was I doing down here? I was finding the X location, it looks like, of each of these nodes. Here, let's write this, go over here, and let's make it one more time. That's what we got. I need that first if. So let's go through. And let's see, you're talking about this if right here. Yeah, I definitely need that one. So let's do Mirage. Okay, let's see. Okay, so now the internal nodes are being drawn. I'm not exactly sure why. Okay. So if we're at a node, we then, let me think. One second. Hey, Pretty let's see, keep the root X equals X. Delete the if. Oh, I see. I see what you're saying. Sure. Okay. Let's remove this, remove that. Okay. Root X equals X, which means when we draw the internal nodes, we no longer have to find an X position for them. So let me see, where are our internal nodes? Here. So we no longer have to find the X position. So let's see, where's Ori 2X? Visualizing the first line. Animate line, let me think. Actually, you're right. We can just find all the X and Y positions here. So let's go through, and we can still split up and draw external and draw internal. That's perfectly fine. Okay, you're right. So let's go through here, and let's give them all a Y position. Okay, so here's what we're going to do. We don't need a node parent X anymore, nor do we have to worry about, yeah, so we don't need the node parent X, but we do need the node parent weight. Let me see, node parent Y, that's no longer necessary. We can get rid of that and bring it down here. Okay, visualizing the first line. So we're going to say ori.x is node X, ori.y is node Y. That should be fine. I think we need that. Okay, so now let's go through and let's see what we have. So let me go to the depth first search guy again. Yeah, that's actually exactly what we need to do. You're totally right about this. And this actually gives us a very simple command that we can work with, much less complicated. So this is much better in the end. So we want int level. Now what we're going to do is, let's see, we do level +1 in there. So now we're going to say root y, and let's do the level thing here. Root pointing to y is going to be equal to, how did you do the y positions here? Let me see, level +1, draw point, level plus dy. Oh, okay, so you created some arbitrary starting y. So I guess we'll just say this is going to be equal to times dy, and I'll set dy arbitrarily to 25. Okay, so then we go down here, draw tree. Yeah, okay, so everything else should be set. Okay, so this should give us an x and y position for every single point. Now let's just go through and draw them all. So where are we doing? What are we doing? We want draw internal and draw external. Let's start with draw external. We're no longer going to need find x position or any of that kind of stuff. So let's see what we got here. Find vector position external nodes. Huffman tree, lowest location. Yeah, so a lot of this stuff is now unnecessary. So we have temp position x, temp position y. Yeah, this is actually perfect. It's exactly what we need. Thanks for the suggestion, Gustorn. Okay, so what do we need to do? We need to do, and actually you're right, because for the very simple Huffman trees, I totally agree with what you're saying. We need a clear tree more than we need one that has significance. But when we're drawing the animation of all of the tree weights changing and things like that for the dynamic Huffman thing, I think we'll need the weights. Yeah. Good. Okay. So this is actually super useful. I'm going to have to gut some of the code though. Since we already have most of this, I think up on github.com, let me run a very quick git diff of Huffman visualization. I think most of it's up on, sorry about that, CPP. Yeah, so I think most of it's already up on github.com. So what I'm going to do is I'm just going to kind of gut the code here. Because we can always go back to our previous version. And just to be super duper safe, I'm going to copy Huffman visualization into a separate code, .cpp. And we're going to, yeah, feel free to ask them, Mr. Mink. So we're going to copy this into Huffman visualization .save .cpp. Forgive me for my bad notation. Now let's go into Huffman visualization .cpp. And let's do it. So let's go down and let's see what we got left to do. So we already have the x and y positions of each of the nodes in some sort of tree. Okay. So now we need to do the draw external and internal stuff. Grow circle, still fine. Animate lines, still fine. Draw external. Okay, so here's where things get a little bit complicated. We have the position of all the external nodes, and we have std string. So what we need to do is find a way to draw this. So we're no longer going to need the x location or the lowest location here because we're doing this a little bit differently. Let's get rid of this. Okay. So now what do we need to do? We need to go through and find all the external nodes. And then we need to draw all the external nodes. So we are reading in frame animation time in Huffman tree, and in the Huffman tree we have the root node. So let me see how we did draw tree one more time. Let's go to draw tree. Here we are, so double node root. One thing that I noticed that I failed to do here is return the root node. So let me see, node root, regenerate nodes. What do we return with regenerated nodes? With regenerated nodes, we return back a node Q. Okay, let me think. Node Q. The node Q was something we used later. So let me do node Q. What did we do this for? So let me go down up to main real quick. This is going to get kind of scattered. I apologize for that. Huffman tree, final tree, regenerated nodes. That's going to give us our node Q. We then do draw external. Did we use regenerated nodes after that? We did for draw internal. Oh, that was actually how I did the internal. I want to start programming. Where should I start? I'm thinking of starting to study informatics, but I've been doing only PLC programming. Well, the thing is, when you start programming, there's a whole bunch of little areas. Walk the tree one more time, store all the nodes, internal and external, in a priority queue, then draw according to that. That's actually not so far off of what we have right now. So we have node queue, regenerated nodes, and that's exactly what we did. That's how I did the internal nodes to begin with, actually. So this is actually not so far off. Okay, so we have node queue regenerated nodes equals regenerated nodes here. We created the regenerated nodes, then we drew the external, and then we drew the internal, and we actually just drew the internal exactly how you draw a Huffman tree. So that's good. I'm sorry, I'm really out of it right now. Okay, so we have the two different layers. Good. Okay, so let's go through and let's see what we need to do. So we have node Q regenerated nodes. Final tree root weight. No, Gustro, neither have I. That's why I'm failing so miserably at this. Mr. Mink, to answer your question, programming is this huge kind of term that means a whole bunch of different things to a lot of different people. For me, what I do with programming is way, way different than what Gustorn does with programming, different than everyone else who's been here today. Everyone does something different with programming. It's like, I don't know, I'd say it's kind of like art in a way. Everyone has their own different style, right? So to say you want to get started programming, that's great. I'm glad that you want to get started programming, but I don't know exactly where you want to go. And so I don't know if we can really give you advice on where to go if we don't really know. You say you want to go to informatics, which is great, but unfortunately I know very little about informatics. So I don't know if I can help with that one. But what I can say is there are probably a whole bunch of good textbooks on the subject that you can find. And maybe Gustorn has better information to give you. Unfortunately, I just don't know much about informatics, so I don't know if I can help very much there. But to start programming in general, that's kind of a hard thing because there's so many different places you can go with programming. So what I might do is I might look it up, and I might send you a message after stream, and we'll see where we can go from there. Okay, so we have draw internal, we have draw external. Okay, so now we have to draw the external nodes. What are we doing with the draw external nodes? Let's go here. And let's see if we can get that one done. And then we'll do the internal nodes after that. So draw external. Let me also look at... let me go to grow circle. What am I doing? We have draw external. Where are we doing this node queue stuff? Let me go down to depth first. And let's get this one step at a time. So depth first search, animation root, regenerated nodes, bitmap. Okay. Let's go down here. What was I doing with regenerated nodes? I was pushing back root. Let's do the same thing up here. So we're going to say void draw tree, and I'm also going to do int level. I'm going to say regenerated nodes. So let's do, where are we? Node queue, regenerated nodes. There we are. Okay. Just find something you like, choose a suitable programming language, and go for it. That's my best advice too. So now let's go down here and let's do regenerated nodes. Okay. And here, regenerated nodes. Okay. Now what's next? We have this. What did I do? I pushed back. Yes, so I pushed back root X. Let me think. So we're going through, we have all the internal and external nodes, right? But all I need, let me see. Yeah, this is fine. So in here we're going to do this, and all we need to do is the following. We're going to do regenerated nodes dot push, and we want root. Okay, good. So this is going to push back all the regenerated nodes. This should be fine. Now we can put the draw tree command in here instead of depth first search. So let's do draw tree. Of the following. So we want x, which is going to be anim.resolution x divided by 2.0. I'm just going to multiply this by 0.5 times 0.5. Then we want root 0 regenerated nodes. Okay, there we go. This should draw the tree just fine. Okay, so now what's next? We have to, with the, what do we need to do? Now we have to draw the external nodes. So let's go back to that, and let's see how far we can get. Okay, and guys, I apologize. Today was super scattered because I was just super out of it, and that happens sometimes. I totally apologize. Now that the sun's out, I'm getting a little bit of that vitamin D or whatever the sun gives you. It's getting a little bit better, but I'm still significantly out of it. So now we no longer need this find x position, and again, because we saved everything, I'm just going to go ahead and get rid of this function entirely, just to kind of clean up the code a little bit. Now, let's go through. Don't worry, I can't think tonight. Draw external. So we have vector position of external nodes, and then we have string of all the characters. So what did I do? I went through and found all the temp position y's. Let me see. And all the temp position x's. So what we need to do is we need to read in. We have the Huffman tree. Let's see. Why don't we go and read through the priority queue? No, we have the tree. And we have all the X positions in each of the nodes on the tree. So the tree has all the X and Y positions we need. Now we just have to figure out if we are on an external node or not. So why don't I just do this? Why don't, instead of draw a tree, I just go ahead and draw the external node there in the draw tree command. Yeah, I mean, that seems logical to me, right? Does that seems logic? Yeah, that's fine. Crunch bang, no, I'm using arch, but that's fine. It's close enough. So let's see, draw internal. Let's see, what am I doing? Draw tree, that's what I want, draw. Actually, let me draw external. Let me copy this, and we're gonna take what we need and put it into draw tree. Okay, draw tree is there, and it is also here. So let me go here, pop this down there. Okay, so we're not gonna need these vector of positions. Remove all these guys. Temp position's not needed. We don't need this. Temp position Y. We already have a Y and X position, presumably. Temp position X, external nodes push back. Nope, none of this is needed. Bitmap.size, nope. Okay, here's what we need, grow circle. So instead of going through here like this, let's go through it like this. So we're gonna say is, I just thought, just go through the priority queue. Yeah, to draw the connecting lines, I totally agree. Yeah, I agree with drawing the connecting lines. Okay, so let's go down here, and let's say if we don't have a root.weight. I'm sorry, I don't know why I just said that. Root left and root right. We go here, we grow the circle at the appropriate location. Okay, now what do we need to read in to make this work? We need to read in the animation frame. Okay, so let me think. Current set source RGB, and I think everything else should work. Frame context. As long as we have anim. Yes, so as long as we have anim, everything else should work. So let's go down here and let's read in anim at the very start here. It should be frame anim. Which, anime, wow. Shows which country I'm in. Okay, so let's go down here to node queue. Pop this down to the next line. And now let's fix the draw tree command up top here. And so we want anim here. And now let's take this and bring it up to the top to the draw tree command. Draw tree. Okay, so let's go there. Draw tree. And let's, I guess, just delete this. Put it down here. There. Add in a semicolon. Okay, so now we don't need draw external anymore because draw external should be done with this. I'm sorry, this is probably super confusing to follow, but that's how it is. So let's do draw external. No, we no longer need that. We need regenerate nodes. We need layer 1. Okay, this is kind of confusing. I don't even know why I thought that would work. Let me go to 305. This is draw external. Let's just remove draw external for now. I don't know what I'm doing anymore. Okay, let's go down here. Gosh, I'm so out of it. Let's see, 312. That's within this, but I thought I commented you out. Oh, make. What's the next one? We have 444. String PNG base. What? There we go. Okay. Could not convert 5. 1 second. Where are we? Could not convert x plus 5.0 e to the negative 1 times x from double to frame. Fair enough. Okay, 1 second. Anim. Okay, what's next? Anim was not declared in this scope. Grow circle. Oh. My bad. Oh gosh, this is such bad coding. Let me go to make. Let me see, what do we have now? 451. Grow circle, animation, external nodes, I. That's not the appropriate thing. We need grow circle. Instead of external nodes of I, let me think. What do we need here? We need an X and Y location. Show text. What do I do with grow circle? Here it is. There it is. Here it is here. Double time. Position. Ori. Good. So I need to give it a position. Good. Okay, so let's go down to draw tree. Okay, so draw tree, animation, animation resolution, X, root, wrong. Grow circle. External nodes dot size, time divided by external nodes dot size. Let's just give this a standard time to work with, which will be, I guess, just 2 frames. Why not? External nodes of I. This needs to be changed to a new position. So let's go here. And let's say position, origin. Why not? Yes, I can do that. I can totally do that. I will do that in a bit. In fact, let me write that down as something I need to get done, because there's going to be a lot of things I think we need to clean up tomorrow. Today was super messy, and I have to apologize for that. However, we are getting to the point now where this makes a good bit of sense. So store position instead of X, Y. Okay, so what I'm going to do is I'm going to do this super rough for now, because this whole day has been super rough. We're going to get the external nodes drawn. We're going to call it for the day. We're going to come back and draw the internal nodes tomorrow. That's the best way to do it. Let's do it. So we're going to say position ori is going to be equal to, yeah, fine. Then we're going to say ori.x. It's going to be equal to root pointing to x. And then we say ori.y equals root pointing to y. Okay, so now instead of this, we need to read in ori, which again is the origin. I just keep calling it ori, I don't know why. So we can say origin. Okay, now what do we have? Carry set source RGB, placing text in circle. Characters was not declared in this scope. Characters.cstring. Okay, let me see. That's because we don't need characters.keystrings. C-string, we need key. So we need root pointing to key, because it should have a key. External nodes.x. We don't have any of the external nodes, I don't believe. No, anything that has a y we don't have. So let me think. External nodes.x, textbox.width. So this, instead of being external nodes, it should just be ori.x. And this should be ori.y. Okay, frame context. Anything else? Characters of I. This is now going to be root pointing to key. This is super messy. I'm really sorry, guys. Root pointing to key. Convert from char to constant. Oh, shoot. This is going to be another one of those weird situations. How do we get this done before? I think we had to do something really stupid here. So it doesn't like taking a character and turning it into a constant character star. So we had to do something really stupid before, which was store the key as a string and then do a .c string. So let me see, what did we do last time? So we have depth for search. Nope, I want to do draw external. That's draw internal, draw external. So we did vector position, characters. Oh, we did std string. Okay, characters. And then we went through and we said, how do we increase the characters? Characters of I, where are we? 1 second. Characters. There we are. Next, characters, pushback key first. Okay. So we're gonna do char test equals root key. Okay, fair enough. Let's do that. Let's do regenerate nodes, draw tree. Okay, so we're gonna do character. I think I tried that. For some reason it didn't work. Char, why not? Test works just fine. Equals root pointing to key. Oh, okay, that's fine then. Let's just do the following. Let's say, let me just try this. Char test following is going to be equal to root pointing to key. Then we want the end character. Yeah, null terminator. Yep. Okay, so now instead of root key, we're going to read in test, and let's see what happens. I had so much trouble with this last time, guys. So root key, we want test. See what happens if we make that. Warning. We got a problem. Let me go to the top. Let me see. In function depth first search, which we shouldn't be using. So let me go to depth. Where are we? Depth first search. Depth first search. Void depth first search. Depth first search. Only in depth first search. Okay, let me see. In function depth first search. Frame node. Exit 1 status. Let me see. Huffman visualization for undefined reference to find X position. Oh, okay, fair enough. Let me do that. Where's find X position? X position. Right here. Temp position X, draw external. Well, that's not being used anymore. Find X position. Depth first search. That's not being used anymore. You deleted the definition. That's a linker error. Find X position, not declared in this scope. Ah, fair enough. Okay, so let me do this. We have everything stored, right? Okay, that's fine. Let's do it. Depth first search. Where are you? Remove you. Depth first search. Remove you. You guys are all dead now. At least to me, anyway. Okay. Come on. Still a little bit longer. There we go. Make... Woo! Okay, now let's see how badly it broke. Obviously, the internal nodes are not going to be drawn correctly, but the external nodes might be. So let's go to Mirage animation.gif. Huh. Well, that was a little different than how I expected it to happen. Yeah, I can't honestly say I expected that. Interesting. Yep. Not sure what we're looking at here, but that's okay. Okay. So let's see what we got to do. So the internal nodes are clearly being drawn incorrectly. So for now, I'm going to just go ahead and not draw the internal nodes. And we're going to worry about the internal nodes tomorrow. Let's see if we can get the external nodes finished. And then we'll worry about the internal nodes again. I apologize for this. Today was kind of a weird, long drawn out stream, but I think we're finally kind of starting to get there. Okay. So draw internal. Let's go ahead and not draw the internal nodes. And let's see, what do we need to do? Continue with the draw tree command. So where is draw tree? Grow circle. We should have at the end of draw circle. Let me see, animation current frames plus equals draw frames. Yes. So we do have that. Now, let me go down and let me see what the draw frames are. So let's go down to draw tree. And let's see, draw tree animation resolution X plus 0.5 root. Okay, down one more. And we should have grow circle. Let's see what happens if I do, instead of 2, let's change this to 10. And let's make it one more time. Now this will do everything but the external nodes. And again, we're running into a bit of a situation here where all of the nodes are drawn at the same time. Is that okay? Maybe. We'll see what we want to do from here. Some animation. Yeah, so they're all being drawn at the exact same time. I mean, it doesn't look bad. It's just a little bit different than how I anticipated it to go. And the nodes are in clearly different positions here, which, yeah, I'm not sure. So some nodes are still being drawn on top of each other. That's an issue. Let's change this to 1 frame a second. Let's go over here, Mirage frame animation.gif. Oops, I totally forgot to make it. Make. Oh gosh, this is great. Okay, so let's see what we got. Let's go ahead and, what am I doing? Let's do this. Mirage animation. Why needs more spacing? Yes, we'll worry about that in just a second. Yeah, so why are they all appearing at the same time? Okay, so that is an issue with, we're reading an animation. Okay. Oh, you know what? Maybe I need to do something real quick. Let me change draw tree so that we read an animation, but there's an %, there. Okay, now let's, what do I need to do? Go up to the top, look for draw tree, and let's add an % after this. Okay. Now, maybe, and I'm not placing any bets on this one, but maybe the issue is that we weren't returning back the appropriate, we didn't actually change the internal animations. So let's see. Oh, there we go. Okay. This is actually doing what we wanted to do. It's kind of slow, and the X positions are clearly on top of each other still, but that's something we can fix a little bit later. Okay. We're kind of getting there. Kind of getting there. Okay. So let's go down, and let me see. Why are the frames being drawn so slowly? So let's see. Grow circle. Draw frames. Animate line. That's not what I want. Draw external. That's not even being used anymore. Draw internal. Hey, Zivo25, what's up? Okay, I want to go to draw tree. Here we are there. And of course there. Okay, so we're giving it exactly 1 frame to draw this on. So I've got a feeling I'm doing this incorrectly. I think this is 1 second that I gave it. What I actually want to give it is the following. So let me do animation.fps, which is frames per second. And then I want to multiply this by the amount of time that I want. So let's multiply it by 0.01. 0.1, let's say. Write this, go over here to make, and let's see what we got. You're fine. We'll be ending in a few minutes, but I'll do a recap of what we did today in just a second. Thanks for coming in, man. So let's do Mirage frames animation.gif. It's still kind of slow. Let me see. Animation FPS is probably like 10. Oh, so we just gave it the same number as before. Wait, let me go to grow circle. Oops, my bad. Grow circle. What do we have here? Grow circle is there, of course. Next, grow circle is here. We do time divided by external nodes.size. What is time? Grow circle, double time. In draw frames is time, animation FPS. So let's say I want these to draw in 0.1 seconds. So let's go to the next grow circle command. There. Okay, so let's give it just 0.1 seconds to draw. I'm assuming they're in units of seconds. Yeah, probably. Why wouldn't they be, right? Okay, now let's see what happens. So we're going to watch this animation. Okay, Mirage animation.gif. There we go. Okay, they're all appearing appropriately. So now let's give it 0.1 seconds to draw, or 0.5 seconds. No, 0.25. Those were a little bit fast. Let's do Mirage animation, no, make. Okay, and then once they're all drawn, you'll clearly see that some of them are drawing on top of each other, which is unfortunate, but that's how it happens sometimes. So then we have to figure out how to fix that. Mirage animation.gif. Okay, so we are drawing all the nodes. A couple things to fix. Let's go up to the top, and let's go to nodes. This will be used for the Cairo package, hopefully subroutine. That's fine. Let's add some new nodes. Okay, so let me go up here and add a few spaces here. There. And now let me add a note here. So, in draw tree, nodes are being overwritten. Okay. Then we have to go down here. Draw internal still needs to be completed. And then what else do we have? One more thing we have to write down before ending the stream. Check Y positions in draw tree. Okay, so these are things that we can fix tomorrow, guys. But for now, I think we can go ahead and close the stream. I realized today was a little bit hit and miss. I apologize for being in and out of it pretty much this entire day. If your condition is your condition correct? I think you're drawing internal nodes. You know, maybe you're right. Let me see. Let's go down to draw tree. Draw tree. Well, the chart test thing had to have worked, right? Because we have letters on each of these dots, right? So I guess I don't understand how we could have possibly... So here's the thing. We say if we don't have a left or a right, right? If we don't have a left or a right, then we say ori.x and ori.y are going to be equal. So the origin is going to be root x and root y. Okay? Where root y is going to level times 25. One had an empty square. Yeah, it did. So the empty square up here, I think that's a space. Because the space is the most used. So it kind of makes sense that it's higher than everything else. Watch the beginning of the animation. Oh, the square. Yeah, there is one with a square. This one. Yeah, there is totally one with a square. You're talking about this one. This square right here. I think that's because I cannot render that one. I think that's the new line. So I have to find a way to render that one, because the phrase that I read in was, Jack and Jill went up a hill to fetch a pail of water. Jack fell down and broke his crown, and Jill came tumbling after. And then I put down a new line and a woo. And I think this is the new line character. That's what I think it is. But I have to be drawing them, right? Because we are grabbing the key directly from the node that we're visualizing, right? So, I don't know. Anyway, actually, I think we have made significant progress today. And we've changed around a lot of the code, internal dynamics and things like that. And we've got a lot left to do. We need to completely gut the draw external, and then we need to rewrite the draw internal. Then we have to figure out the best way to locate all of these X and Y nodes. So let's go ahead and figure that out. Or I'll think about it more tonight, and we'll see if we can figure it out tomorrow on stream. Again, I thought I had this figured out coming into stream today, but then I ran into some situations, or I ran into a situation where I clearly did not in stream. So that's how it happens sometimes. Anyway, guys, I'm going to go ahead and end the stream here. So have a fantastic day, night, afternoon, morning, evening, whatever time it happens to be your time. And I'll see you around next time, where we hopefully make sense of all the stuff we did today. Apologize, I was moving like a million miles a minute sometimes and 0 miles an hour next time. But that's okay. No, it's okay, Zivo. I mean, you had some fun with old friends, right? So that's way more important than coming to a programming stream on Twitch. Guys, have a fantastic day, night, afternoon, morning, evening, whatever time it has to be your time. And I will see you around next time. Have a fantastic time. Bye, guys. Thanks again for coming in.